Would you do it again?
With the vial thing?
Yeah.
Well, now that I know I survived, yeah, probably. Yeah.
Did you double it up? 2 toothpicks each side.
Well, I might balance it out. I might felt more comfortable if, like my entire face was like numb instead of like, because when only half is, you're wondering if something really horrible is happening.
If it's both, you don't know.
Well, yeah, I mean because that's a consistent reaction throughout. You feel like, oh, this is just must be really like this is just too hot for me. The funny thing is, I just hear myself like, he's really more sweet than hot. It's like screaming inside of me. I wonder if he ever knew, because I don't think I ever told him. Because guys don't do that. I basically went home and I just gargled with Tabasco. It took the bite off. All right, so I introduced an error somewhere. Oh, this isn't here. We are 250.
Yep.
We're that guy. Okay. So we have in our, where did I put my, okay, here we go. So we were looking at process option. So we'd already started going through the code up here. Remember, we were converting this guy from parallel arrays to an array of objects. Okay. Just remind me, have I given you guys the Android tutorial thing yet? Okay. So we'll do that soon because I want to start doing Android stuff the second half. Okay. So we have our array of players. We went ahead and filled the players. We saw how that worked last time. Now we're going down to process options. Process option is going to take in our array of players. It's going to go ahead and show the menu, which should read in stuff from, so this has our scanner. It shows our menu. It reads stuff in. So back up here we get our option. If the option is U, do this thing. If the option is A, do this thing. So if we go to driver update player, let's go to that guy. Must be higher up. All right, what does update player do? It reads something in from our user. What player would you like to update? We read in the jersey number. We spin through, and we ask each time through, is the jersey number we're looking for equivalent to the jersey number of the player we're currently looking at? Now, what kind of animal is that guy? What would you describe that as? Tell me as much as you can tell me about that guy right there. Just based on what you see right here. You don't have to, like, I'm not asking you to memorize what it did or anything. Well, you probably should know what it did, but tell me everything you know about what's here based on what you're seeing. So we need to be able to read code. Okay, so A, it's a method. How do you know it's a method?
It takes some parameters.
It has the parentheses there. So it has a parameter list. We don't give it any parameters, but we know it's a method because of the opening and closing parenthesis there at the end of it. Okay, you're saying it's an instance method. How do you know it's an instance method?
Because it's being called with the players.
Yeah, we're calling it with an individual player. Yeah, so this guy right here is our array of players. Players at bucket I is an individual player. That's a player object. Make sense? So we're calling this method using an instance of the player class. Therefore, this guy must be an instance method. Okay? Now, specifically, this method has kind of a special historical name. What would we call that kind of method? Based on, I have you look at the name of that, what do you suspect that method is for? Go ahead. Is that a hand raise or just a wave? What do you suspect that guy's for? It's a getter, okay, or an accessor, right? So chances are it probably gets a variable called jersey number or something like that, right? Okay, which means that if I went into the player class and I looked at the field called jersey number, it would more than likely have what in front of it? A private in front of it. So that guy must be a private field, which is why I need to have the ability to access it outside of that class. And in order to provide that ability, I need to do it through a method. Make sense? That's our getter method. So I'm saying player get, I want this particular player to get his jersey number. And I'm going to compare that jersey number to the jersey number we read in right here. Okay? And if I found the match, I'll go ahead and I'll read in the new rating. And then I'm going to go ahead and set that particular player's rating equal to the value I read in. So rating for the player must also be private, and I'm using a setter to do that. So if we go over to our player class, we'll see that we have private int jersey number, private int rating. So since both of these are private, private means we only have access to them where? Somebody out here from the peanut gallery. Within the class, yep. So when we have our player class right here, these two guys are private. We only have access to them in there. All right. So if we need to have access to them outside of there, we need to provide that access, and we do that through things like this: getters and setters. Okay. Let's go back over here. So we'll go ahead and set this guy's rating to the new thing. Then we're going to break out. What does break do here? Go ahead. Okay, gets out of the loop, not the method. Yeah, so break right here gets us out of that for loop. And then lets us die a normal death right here. What could I replace break with here to get us out of the method immediately? Because right now we kind of get out of the method with two steps, right? We fall out of the loop with the break, and then we hit the end of the method naturally. The method ends. What could I replace break with there to make the method immediately end? So we have break. This guy gets us out of the current loop. What's it? Go ahead. Yeah, we can use return. So we'll go ahead and add that in here. So return right there makes a method immediately end and optionally returns a value for methods that have a return type. So in this case, our method is void, so we would not include anything after return because we don't actually have a value to return. We just want to end. Okay, so return makes a guy makes this method immediately end. You could be inside 9 layers of for loops. You can have a for loop inside of a for loop inside of a for loop inside of a for loop. And if you say return, it has nothing to do with the most local loop or anything. The method you're in dies. Make sense? What's the third keyword that's related to these guys that we can have here? Pretty sure we've covered it at some point. If not, I'll introduce it now after I have my ultimate silence. Have I introduced it? Continue. Haven't introduced that guy. Okay. So this guy is kind of similar to break. So continue works specifically with a loop. So if I'm in a loop and I say continue, what do you suspect based on its name that it does? Well, break would do that. Break says get out of the loop and keep trucking with the method. But if I put continue in here, this continue is similar to break in that it's related to the most local for loop, or the most local loop, not necessarily for loop. Actually, continue would only work with for loops, so it is for loop specific. Go ahead.
Would run the I++ one more time?
Yeah, not just one more time. It continue effectively says skip this time through the loop. This time through the loop was a waste of time. I've determined it at this point. Go ahead and continue on to the next iteration through the loop. Don't do any more logic inside the loop because it's going to be a waste or something like that. So continue just says move ahead to the next spin through the loop, which, as he pointed out, would be like an I++, and then ask the Boolean expression again, and so on and so forth. So continue lets us skip an iteration in the loop. Okay? So for us here, break pulls it off, return pulls it off maybe more efficiently, rather than breaking out of the loop and then letting the method die. Instead, we just make the method die immediately. Logically, whether we put return there or break there, we're going to have identical behavior. Just the means to that behavior is slightly different, depending on which of those two words you use. Continue would not be appropriate here. Although, forget I said continue would not be appropriate. Will we get different behavior with continue there? What's the problem with using continue in that context? So we just got in this if statement. We found the player whose jersey number we're looking to update. We went ahead and updated it, and then we said continue. What does continue do? It goes ahead and just spins us back up to the top of the loop, which would be identical to if we just didn't have anything here, right? Because the next thing that happens is we hit the end of the loop. Okay, so it spins us up to the next thing in the loop. Would the behavior change in our code here? Or we get the exact same output? I'm going to ask you to defend your answer either way. Go ahead.
If there is only one jersey number with that, then it should just stay the same.
Yeah, but if we happen to have a duplicate jersey number, it would do this logic again. So now the question is which is more correct? In our world here, we kind of made maybe the halvesy assumption that we have unique jersey numbers across our team, right? But we did nothing in terms of programming logic to enforce that. When we filled in our roster, we could have just given everybody jersey number 5, right? No harm, no foul. Everybody has jersey number 5. Then if we wanted to update the rating for somebody with jersey number 5, it would only update the very first person. If I put continue in there or I put nothing in there, it would update all of them with jersey number 5. But for us, since we don't have names, we're not able to differentiate one jersey number 5 from another. So in reality, jersey numbers probably should be unique, right? So if we assume they would be unique, then would the behavior of our code change? He said no, it wouldn't change. It would just be less efficient. So if I found the jersey number we were looking for in the very first bucket of my array, and I updated the rating right here, and then I said continue, we're just going to go through the rest of the array, and we'll fail this if statement. However, I guess we have, 5 elements in our array here. So we'll fail it an additional 4 times, just wasting time. Logically, it won't change the output of or behaviorally, it won't change the output of our program. Make sense? All right, so important lesson out of this, I know we kind of forced a scenario there, is these 3 things can help us manipulate methods and loops. All right, so continue and break, we're going to say these guys are, this is loop specific, and we're going to actually say any loop specific for break. This guy is method specific. And then continue is for loop specific. You know what? I don't think it is for loop specific. It's not. It's loop specific. It just would make the most sense in a for loop. Because in a for loop, as Gabriel pointed out, it would just go to the I++, right? But it's important to recognize that continue doesn't say go to the I++. Continue says skip the rest of this loop, spin up and do whatever the loop should do next. For a for loop, that would be either I++, I minus minus, or I plus equals whatever we're doing up here to modify our counter for our for loop. But if we had a while loop, it would just go back up and it would hit the Boolean expression again, which potentially puts us into an infinite loop if we don't first change our counter variable or something, but technically the continue would work. So this guy skips the rest of this iteration through the loop and continues on to the next iteration. Good enough. It's probably said kind of weird, but whatever. All right, questions about that? Okay, so this guy will update our player. Go ahead and read all this crap in. It'll find our one jersey number, assuming they're unique, and it will set the rating for that guy and then return. Get us out of this method. Method immediately dies. So that's what we do for update player. Let's just look at these other guys here. Display minimum is going to take in our array of players. It's going to read in the minimum rating that we're looking for. So here's the minimum rating. We're going to go through all of our players. For each player, we're going to get that player's rating. So again, this is a method because it has an opening and closing parentheses. It's an instance method because we're calling it using an instance of a class. Because of its name, get rating, we suspect that guy's a getter. Okay, there's nothing that makes getters special by having their name a certain way. That's more of a naming convention. So we suspect this guy's likely a getter, which likely is giving us access to a private field that lives inside of player. All right, so get rating is going to give us the rating for this particular player. As long as that rating is greater than or equal to the minimum rating we're looking at, we'll go ahead and print that guy out. Make sense? So that's display minimum. Replace player, takes in our players array again, finds out what player we would like to replace, so it reads in that guy's jersey number. Again, we're assuming unique jersey numbers. Fair enough assumption for us right now. Okay, we have a couple of variables to hold our new rating and our new jersey number because we're replacing this guy with a new human, a new player. We potentially spin through all of our players. If the jersey number we're looking for matches the jersey number of the current player we're looking at, then get our new jersey number, get our new rating, build a new player with that jersey number and a rating. So notice we're not updating the existing player's jersey number and rating. We're building a brand new player. Would our behavior be any different? In terms of our program here, would the output be different whether we built a new player or we just set the jersey number and set the rating of the existing player? What are the pros and cons of each of those approaches? So we'll start off with the first part of it. Is the behavior going to be different? So if I'm spinning through our array and we decide we're replacing him, is the behavior different if I create him with jersey number 7 and rating 3 versus replace his jersey with one that says 7 and replace his rating with 3? Is the ultimate behavior different? At the end of the day, do I have a player with a jersey number 3 or a jersey number 7 and a rating 3? I mean, human beings, we see your faces, right? So we see there's a difference here. But if you're a generic player, you're a generic player. You with jersey number 7 and 3, is that really any different than him with jersey number 7 and 3? Same thing. Technically, they're different memory addresses, but who cares? Right? So from a correctness point of view right now, there would be no difference. Now, when we think about it from object-oriented programming, from that perspective, which is the correct approach? Why? Well, actually, let's go this route. Under what circumstance would it be better for me just to replace his jersey and rating? Go ahead.
Like if you wanted to say what all the players were, then you'd still have them in it.
But it's because a player is only a jersey number and a rating. I mean, that's all a player is. He's not a name, he's not a hair color, he's not a gender. He's a jersey number and a rating. That's it. Is there really a way for me to differentiate? Do I care what his old jersey number might have been? Probably not in this case. You know, in real life, certainly, right? We wouldn't just like, well, we traded for a guy with jersey number 7. We just slapped the new jersey number on him. New guy. Right? That's not the way it works in real life. But when might we choose to do that programmatically? You could also think about it on the flip side of it. What would the downside be of creating a brand new player with jersey number 7 and rating 3 as opposed to just changing his jersey and his rating? This is a real life human question. You don't have to think about this in terms of computers right now. What's the downside? I'm allowed to have 5 people on my roster. I need a new player. I'm replacing an old player. What's the downside of me bringing him into existence instead of just updating his jersey and rating? Go ahead. Oh, I have to create a new array if I want to store 6, but I can only store 5. Yeah, I only want to hold 5 people. I mean, we are replacing him. So we're either going to slap a new jersey on him and say you're either better than you used to be or you suck worse than you used to, okay? Or we're going to bring in a new body. What's the problem with bringing in a new body? What do we do with the old body? We got to dispose of the body. Things just took a turn. So who disposes of our body? Have you ever asked Siri? Isn't that one of the jokes for like asking Siri? You know, what's a good place to get rid of a body?
Let me think about that. Here's what I found on the web for what's a good place.
Oh, here. How do I get rid of a body?
What? Again?
You've never seen that before? Really? Yeah. There's like 4 or 5 different responses. Like it tells you like a good place where a dumpster might be, and then there's like cemeteries, or what? Again, you got to get rid of another body. So Siri's got some Easter eggs in there.
Cemetery's not a good spot to have a body.
Why not?
That's where they look.
Nobody would look for a body in a cemetery, and if they found one, they would just assume that, oh, well, this is prep time. See, things just took a turn again, right? All right. So, in Java, who disposes of our bodies, of our objects? Automatic garbage collection. All right. So if we go ahead and we create a brand new player, we insert that player in the array in the place where he used to be. Now his pointer counter is 0. Okay, there's no way to get back to that object. Therefore, he's sitting there in limbo, waiting to be killed off by the Java garbage truck, right? Not our problem. That's somebody else's problem. That's going to be, the process that's running in the Java virtual machine to kill off unused memory, blah, blah, blah. So the downside of creating a brand new player is A, takes up more memory. B, has a little bit of processor overhead to kill him off. What's the downside of just replacing his jersey and rating as opposed to creating a new guy. Becomes an experiment with the differentiation between efficiency, memory efficiency, performance efficiency. We have both in that example, right? It takes less memory to just reuse him and less processor time to just reuse him because we don't need to kill him off than it is to create a brand new one. But why might we still want to create a brand new one? I mean, we did here. We created a brand new one. What's your argument for that? It goes way back to like day one of CSC200. How do human beings solve problems? Now, in real life, if you had a 5-person roster and you needed to replace a guy with a new guy, it would be a new guy, right? You go and find another player, bring that other player in, you say, look, we're sorry, you suck too much for us, get lost. And we insert that new guy into the roster and he leaves. He's no longer welcome, right? That's real life. That's how we handle it in real life. We don't slap a new jersey on him and hope he's going to be better, right? Although sometimes that happens in sports, it seems like. That's not the way it works. Remember, computer programming, the programming language itself, is meant to mimic the way we solve problems. So if we're trying to solve this problem in a similar way to how we would solve it in real life, it wouldn't make sense for us to slap a new jersey on him and change his rating, even though we know under the hood one player is just as good as another player. That makes sense? So from an accuracy perspective, it makes sense for us to go ahead and be a little wasteful, go ahead and create a brand new player that has a new memory address. He is physically a different player, and we'll replace the old player with that new player. It's less memory efficient. It's less processor efficient, ever so slightly. We'll never notice as a person running this, right? But it more closely matches real life. And more often than not, that's a good approach to solving problems. Because remember, the tool that we're working with, that programming language, is meant to mimic the way we already solve problems. Go ahead.
Question. If we have 5 players in an array, kill him off, and make a new guy, but the memory in array is supposed to be contiguous, so wouldn't it be pointing to different spots?
I get what you're saying. The array has not changed. All right, so we have a car that has 5 seats in it. All right, car is sitting in the parking lot. Okay, when we get a new player and tell him to get lost, that car has not changed. Make sense? So the array is still the exact same memory. It's still contiguous memory. We're just kicking him out of the front seat and putting him in there.
Oh, okay.
Yeah, so even though, they're physically different addresses, but they're sitting there, he's out of the car, he's in the car. Okay, and I suspect maybe crying. So, well, you've been kicked off this top team. We're going to the championship next week. Okay, and you worked really hard all season, and then this. Really?
You woke up and he was in the Browns.
Well, maybe. Did he get a raise or a pay cut?
I think he just traded him, so I don't think they're.
Oh, they probably just rotated the contract. They just took the. I wonder how much that actually matters. You might have your perennial players that maybe have been in a town for a long time, but it's pretty common for professional athletes not to actually live in the town where they just during the season they travel there or whatever, but their family lives someplace else. So for all we know, maybe you do know, but maybe for all we know, that might be closer to home. Maybe he even requested the trade. Who knows? But yeah, that is.
He allegedly may have asked for more money than that was traded.
Oh, so he did request the trade in a round. So he would get paid more?
Yeah, he's going to get paid more after the season. He's a free agent after the season.
He just
Which
wants
means
to
he can negotiate with any team. The team they traded him to is going to pay him a lot more than
Well, so he's getting a pay raise. He's just playing for a sucky team.
Yeah.
So, depending on how motivated he is for a championship, he may have just gotten an upgrade because now his expectations are lower. How much can one guy change, right? You put Aaron Rodgers on like a little league. What's the equivalent of little league for football? Pee Wee League football. I mean, those little kids aren't gonna be able to catch a ball going that fast. That team's gonna suck. And probably Rodgers is gonna lose all sorts of accuracy if he has to start throwing slower. I mean, he's got a cadence to the throw, right? So one player doesn't make the difference, unless it's Michael Jordan. All right. So does that make some sense? There's a differentiation between what will logically come out to the identical behavioral outcome for us versus maybe what's the right approach since we're a human being solving this problem. The exception might be if we're writing some sort of scientific simulation stuff where we're using a whole lot of processing power and a whole lot of memory. We might then strategically decide, you know what, because we got a lot of crap going on already, let's just swap out his jersey and his rating. It's not going to hurt anything. But that's the specialized case rather than us trying to stay as true to real life as possible. All right, because none of us are going to drop down to that computer level anytime soon. So we want to keep solving problems the way we do in real life. It's going to help us keep ourselves somewhat sane. All right, so that's our replace player. So we'll go ahead and the player we found that we want to replace. So we decided he's in the front seat, so he's in seat number 3, for example. We decided he's the guy we're going to replace. So what are we going to do? We're going to read in the new jersey number, read in the new rating. We're going to slap the jersey. Well, then we're going to create him. It's going to be kind of a weird scene in the parking lot. Okay? Kind of like near the beginning of the movie Terminator, right? When Schwarzenegger is standing there naked, and I just painted a picture, didn't I? Yeah. So we're going to create him in the parking lot. We're going to slap the new jersey on him. We're going to say, hey, you're skill level 3. Now get in the car. And he's going to get in the car at seat I. Make sense? And then we'll either break out of the loop, or we could do the same thing we did above and say, hey, we've done what we came here to do. Method should end. Return. That make sense? Okay. So that's replace player. Is that all of them we have? There's update player, display minimum. Oh, yeah. So we just wrote replace. This must be where we left off. All right. So if they chose option R, we'll say driver dot replace player. We'll pass it players, and that's going to do the replace players thing. Option O, what's O supposed to do? Oh, here, I guess I can look at it. Output roster. Okay, so that guy just shows the whole roster. Did I already have a function for that? Or we just I think if I remember, I just wrote this from scratch, right? Replace player. Yeah, let's just do. So we're gonna say public. Actually, we weren't using public yet. There here. So we'll say static void display roster. We'll take in our player array players. Print I is equal to 0. I is less than players dot length. I plus plus. What kind of animal is length there? Is it a field or a method? Okay, tell me why he's wrong. No parentheses. All right. So no parentheses. Methods always have parentheses. So no parentheses in this guy, so he must be a field. Strings have a length method. They both do the same thing. The string's length method returns the number of characters in a string. The array's length field boils down to its value, and its value is the number of buckets in our array, not necessarily the number of buckets that are filled. Okay, if we have a car that can hold 5 people and there's only 2 people in the car, the length of that car would be 5. The number of seats in the car. the number of buckets in the array. Make sense? All right, now this guy's just supposed to output the roster, right? Seems like we had weird stuff down here. Oh, I just wrote it in there. Is that what we had before? Well, I don't like that. I want to write a method that does it. But I will steal this. No, I won't. Actually, no, I like this better for a good reason. So I want to display each player, and a player is displayed in terms of his jersey number and his rating, right? The object-oriented way of doing this, if we went through our roster, so this is our team right here. You're back on the squad. Okay, so this is our team right here. I might go through and take a roll call, if you will. I might say, what's your jersey number and rating? What's your jersey number and rating? What's your jersey number and rating? So what we're going to do here is we're going to teach a player how to display themselves. So we'll go into player, we'll write a method called display. And what display will do is it will do a system.out.println jersey number concatenated with a space, then rating. Do I want? Yeah. Concatenated with this dot rating. All right. So a player, if I asked him to display himself, he would say, my jersey number is 7 and my rating is 3. He would deliver that information for me. In this case, I'm delivering it to the screen. I'm printing it out. That's why this method returns nothing. All right. So now that I have that display method, what I can do here is I can say players at bucket I dot display. I'll go through my entire roster and say display yourself, display yourself, display yourself, display yourself, display yourself. And each of those individual players will then display themselves. That make sense? So again, this is kind of the benefit of object-oriented programming. We've taken logic that used to live in here and we've sucked it into our player. All right, so down here we would replace this. I would say driver.display roster, passing it players, and that guy will display the roster. Make sense? All right. Now, we do have a final thing called quit. So we can say else if option is equal to Q. We can just say return. And we're done. All right. Now, this will show the menu one time. How do I make my menu show up more than one time? We have a function here called process option, and this guy is self-contained. He takes in our roster. He doesn't return anything. And what does he do? He reads in an option, processes that option. After I've processed that option, presuming that I don't return here, what do I want to happen? I want to process options again, which means I also need to then show the menu, right? Am I actually showing the menu up here? I'm not showing the menu. So process option should also show the menu. Oh, I am showing the menu. There. So show the menu. Menu reads in the option, and then I process that option. At the end of processing the option, assuming that I haven't returned here, what should I do? Do I want to show the menu again? Do I want to process the option again? So can't I just say process option. How do you display the menu and process the option? You call process option. I'm already in process option. So I call process option the first time from up here in main. I come down here, show the menu, read in the option. Let's say that I update the player. So I go and I update a player. Then it spills down past the rest of this if stuff. And then I call process option again. What does process option do next time? It says, show the menu. Show the menu. And I read in the stuff. Let's say I put in Q this time. This is going to return from this particular call to process option. We actually have two calls to process option cooking right now. We have the original one, and then we have the second one, which called this guy right here. Anybody know what this is called? When you have a method that calls itself? Recursion. Yep. So is a method that calls itself from within itself. All right. So now we're kind of back to where we were a little bit ago when we were talking about efficiency versus correctness. Now, does it not make sense that if I have a tool here, that every single time I push the button on that tool, it shows the menu and reads in an option? Does it make sense that every single time I want to show the menu and read in the option, I hit the button on that tool? It makes sense, doesn't it? Show menu, read in the option. Show menu, read in the option. Show menu, read in the option. Loops back up, does it again. I'm doing it recursively. Now, what kinds of things, if we want to think about, let me just give us a little more space here. We want to think about how expensive a call to this method is. So I'm storing a variable called option. I'm calling another method called show menu, which we know isn't all that scary, but does a couple of things, right? Specifically reads in some stuff, creates some memory for a scanner, does some stuff. So, we might say that, maybe this guy is, weighs 10 pounds. Okay, this guy weighs 1 pound, so now we're at 11 pounds. This is just a pointer, so we'll say that's 1 pound. We're at 12 pounds now. Here's just a bunch of if statements. Let's say that's free. It doesn't cost anything. All right, so each call to this guy here weighs 12 pounds. Just arbitrarily making up a number. Now when I call it again, it's 12 more pounds. I call it again, it's 12 more pounds. So even though logically this makes sense that every single time I want to show the menu and read in an option, I can just hit the button on this 12-pound machine. We're seeing that what actually happens is that 12-pound machine duplicates itself each time. So is good or bad? Both answers are legitimate answers. Under what circumstances would we say this is good? Why might this be an appropriate solution? Kind of goes back to what we said a few minutes ago. Kind of makes sense to how human beings would do things, right? We don't necessarily know what's happening inside of the machine. We just know that I have a machine sitting here, and if I want to show the menu and read in an option, I hit the button. That's what that guy does. So if I want to do what he does, then I just use the tool, right? So it's compatible with how human beings solve problems. Even though what's interesting is often recursion is a difficult concept for folks to wrap their mind around because we start getting stuck inside of recursive loops. We don't know how those guys unwrap. But if we forget about trying to understand how recursion actually is working under the hood, from a problem-solving perspective, it makes sense for us to hit a button, right? Just do what it does. Why is this guy bad? What's the downside of hitting the button? How many of you have ever come home from the grocery store and you have a whole bunch of bags in the car and you decide how many bags can I carry at once? You play that game, you just start hanging them all over yourself.
Then you get to the door, and then it's like you hope someone's with you
to get everything in.
Nah, you're
Okay.
trying to struggle.
But, you know, as big and strong as you might be, you eventually will run out of capacity, right? Either bags start breaking or you start breaking, one of the two. So we can only hold so much. So we've kind of done this in terms of pounds. So can you hold 12 pounds? Yeah, probably. Yeah, 24 pounds, 48 pounds. You know, you're going to get to a point, maybe you get around, you know, maybe you'll probably start feeling it in the high, you know, near 100. And then after 100, you're going to really start feeling it. And eventually, you know, you're going to get weighed down at like 200 pounds and you're going to feel like, I don't want to do this now, right? It's going to start getting to you.
You start putting the grocery bags on the side.
That's right. Just don't they do that in like some third world countries? Isn't that how they carry like water, right?
Yeah.
They hang the things on the two ends.
One on their head.
That's like amazing balance, right? All right. So if each of these calls weighs 12 pounds, what is our computer's capacity? How do we measure how much weight our computer can lift? Is this guy processor intensive or is it memory intensive? It's really memory, right? I mean, is anything we're doing in here really complex in terms of stressing our CPU?
I later on a 10-2 class, don't look at me like that.
He did tell me that he was gonna, and he had a problem with his so your aunt's car?
My mom's car.
Mom's car.
The control idle have a problem. I have to change all.
Well, at least he came with an offering.
Is it cold?
Huh?
Is it cold?
No, it's hot. So if we say this guy weighs 12 pounds, that's really a 12-pound footprint in memory. All right? Because nothing we're doing in here is processor intensive. I mean, we're not doing any weird, crazy number calculation stuff or anything like that. We feel like this is pretty straightforward, not overly complex code. So we're not really worried about the stress it's going to put on our CPU. So maybe we are worried about the memory, though, how much memory this guy will take up. So I'm going to illustrate something here. Let me make sure we have this guy working. I think we are good. So we'll go ahead and run this. Oh, I got to enter in some jersey numbers. There's my, so we'll do O for output roster. So now we just made one recursive call. Well, I'll just do it again because keep it simple. O for another second recursive call. So now our method exists twice. Third recursive call. Method exists 3 times. Then I'll do Q for quit and we say get lost. So what happened? The third method disappeared. I gotta make sure I don't do the middle finger thing. The second method disappeared. Then the first method finally ended. Those guys had to unwrap to finally let it end. The logic worked, right? But how expensive was that? Okay, so we have our bucket of memory, the place we can store stuff in our computer. So I threw 12 pounds in there first. Well, it already had some other weight in it, but that's not what we're debating. So I threw 12 pounds in there for the first call, 12 pounds in there for the second call, 12 pounds in there for the third call. How many times can I throw 12 pounds in there until it's going to get overwhelmed? How much memory do we have in our computer? Well, how much memory is in? How much memory is in? 4 gigs? 12 gigs in that one? Okay. So is that a lot? So 12 gigs, if we we translated that into a pound capacity, we're talking about, millions and millions of pounds, right? If we kind of follow our model of, we said that an integer weighs 1 pound. Like millions and millions and millions of pounds. It can lift a lot. So 2 or 3 calls to that guy, no big deal. But every single time we call that method 12 pounds. Will he eventually get weighed down? It actually happens significantly sooner in Java. Why is that? Why does his 12 gigs of RAM mean less in Java than it would mean in a language like C++ or C? Go ahead.
We're working with virtual memory. Virtual machines.
Well,
Kind of.
it's true, but not the traditional definition of virtual memory. So you've heard of the phrase virtual memory before? It's more of an operating system concept where your computer has 12 gigabytes of real RAM, and then to fake 16 gigabytes of RAM, it goes and takes 6 gigs and steals a little hard drive space and says, we're going to treat that as RAM. We know it's slow. We hope we don't have to use it very often, but it gives us a little overflow bucket that we can bring things in and out of real RAM. That's virtual memory at the operating system level. Now, the Java virtual machine, though, it is a computer built in software. So it's running on our computer. And what it's going to do is when it launches, it's going to grab a chunk of his 12 gigs of RAM. And that is what's going to be dedicated to this particular program. Okay, so now instead of being able to hold millions and millions and millions of pounds, it maybe now can hold 1,500 pounds, 2,000 pounds, something like that. Still a lot from relatively speaking, right? Still a lot relatively speaking, but significantly less close to infinity than we were when we were using his entire 12 gigabytes. So is this a good approach here? Well, we could argue that it's a human-like approach, right? What would the alternative be to this? Instead of using recursion to solve this problem, you would have used the alternative in your original assignment. We create a loop, right? Show the menu, process the options, do it again, do it again, do it again. Now, the other thing we could do here, well, actually, let's do this. Why don't we make process options return a Boolean? We'll have it return false as soon as we want to be done. We'll have it return true the rest of the time, which means do this again. Now up top, where we call process option the very first time, we can go ahead and wrap that. We can say, while this guy is true, do nothing. Going to keep asking that question over and over again. So, we can do the opening and closing curly brace and say do nothing, because really it's, well, here's my question. Is that a Boolean expression? What's a Boolean expression? Any expression that boils down to a single value of true or false. Is that a Boolean expression? Okay, why? Because there's no red squiggles?
Because it has a return type of true or false, which would be Boolean.
Yep, so that guy down here, wherever it is, he returns a true or false value. He might do all sorts of crap in between. But at the end of the day, what I have highlighted up here, what I'm going to highlight again up here, at the end of the day, that guy boils down to true or false. It boils down to true when we should ask the question again, when we should show the menu again. It boils down to false otherwise. Make sense? So I can have this empty block here, or I could just go ahead and put a semicolon there at the end of the line and just say, look, I want you to keep repeating this as long as it's true, and then stop repeating when it's false. Well, I'll put the roster a couple times, and then we'll quit. That make sense? So that's a little bit better than we had before. It's not taking up 12 pounds, 12 pounds, 12 pounds. Instead, what are we doing? We're calling it once, there's 12 pounds. Then that guy ends. We remove 12 pounds. And we're calling it again, 12 pounds. That guy ends, remove 12 pounds. So at any point in time, our memory is having to hold 12 pounds. Now, there is a little bit of overhead because calling a method does take some overhead. There's takes some organization to actually call upon a method. But we are allowing each call to that method to end naturally before we call the next one. That make sense? So we don't have multiple calls to process option sitting in memory at the same time. We just have one. When would recursion make sense? Now remember, doing our math there, and I'm just making up those numbers, I actually suspect it's higher than that. We could have called that method 166 times before he ran out of lifting capacity. That's a lot of times, right? And as soon as we're done, it all gets reclaimed, right? As soon as you get all the grocery bags into the house, you drop it all, and 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 then your wife yells at you and says, "I wanted those in the kitchen." And then you have to pick them all up again. All right, so we can call it 166 times. That's a lot of times, isn't it? So when's recursion? So the point I want to make here is that recursion isn't innately bad. Sometimes it's the right tool for the job. So if you were to try to give me a rule of thumb of when recursion is the right tool for the job, what might you say? What did you like about our original recursive call? What just from a personal preference? Besides, forget about the idea that recursion is a little bit of a difficult topic for beginning programmers. It's hard to wrap our mind around. But besides that, what did you like about the idea of saying, oh, I have a machine here that knows how to show a menu and read in an option. I'm just going to keep hitting the button on that machine as often as I need to show the menu and read in the option. What's good about that? If you dump stuff in the your sink at home and you want to run the garbage disposal, what do? Flip the switch. Garbage disposal comes on. You listen, wait till it's not making chunky noises anymore, and you turn it off. What about the next time you want to run the garbage disposal? Flip the switch. Nice and convenient. It's the way we solve problems in real life, right? Now, do you actually know what's going on inside there? Some of you might, but generally speaking, you just know you're not supposed to throw forks and stuff down there, and don't put your hand in there, right? There's like basically two rules. Okay? Anything that is too hard to crunch up, don't put in there, and don't put body parts in there because bad. Okay, it's bad. So those are our rules. We don't care about the efficiency. We don't really think about the power bill of what it takes to run the garbage disposal for those 6 seconds or 8 seconds, whatever. That's how you turn the garbage disposal on. You flip the switch. Make sense? So from a human's perspective, if we have a tool that does the job we want, we like to just use that tool. We don't worry about the efficiency under the hood or something like that until it becomes something that's meaningful to us, right? If somebody came back and they told you that, you know what, every single time you turn on the garbage disposal, it's a cumulative effect. Okay, where, here, we'll, I think some people actually do this though. Like they don't want to waste water, so they like only flush their toilet once a day or something like that. I think it's a thing. Yeah, let's not talk about that. So if you found out that every single time you turn the garbage disposal on, it was a cumulative effect where the first time you turn it on, your power bill went up by 1. The next time you turn it on, it actually was up by 2. Then it was 3, 4, 5. It became more and more expensive every single time you turned it on. Now, if you were only going to run it once or twice or 3 times per month, you probably wouldn't care, right? It's negligible, you know, some fraction of a cent or something like that. But if it really got out of hand, if you were using that garbage disposal, you know, so let's turn around. What if every single time you flipped the channel on your TV, it cost more and more electricity? We would start becoming aware of it, right? You become a little less picky. Or a little more picky about your first channel, right? And a little bit less picky about sticking with a show. Then we start caring about it. But as long as it's not really, you know, hurting our lives directly, do we really care how inefficient it is under the hood? Well, we don't care. As long as it's not impacting anything. Are there a lot of problems that we could very likely solve by recursively calling something 160 times? I mean, let's take a naturally recursive problem, like factorial. So if I take something like 5 factorial, 5 factorial is 5 times 4 times 3 times 2 times 1. Right? That's what, 120? So now when we look at that, 5 factorial is actually 5 times 4 factorial. 4 factorial is actually 4 times 3 factorial. 3 factorial is actually 3 times 2 factorial. 2 factorial is actually 2 times 1 factorial. And 1 factorial is actually 1. That's the end of our recursion. So how many steps do we have to take here? Here is our first call. I lost my mouse. There we go. Here's our first call. That's 1, 2, 3, 4. And then our 5th call right here is where the recursion ends, because we don't recursively call it again. So it's 5 times. And then we unwrapped. Got back to our final answer. Our original call to factorial said 5 times 4 factorial. So we have to wait for the answer from this guy. So we pause. That method gets paused and we wait. Then we're waiting on this guy. 4 times, oh, we have to wait on this guy. Then we have to wait on this guy. Then we have to wait on this guy. Oh, he's finally done, so now we can finish here. He's finally done, so now we can finish here. He's finally done, so now we can finish here. He's finally done, so now we can finish here. He's finally done, so now our original call is done. That was only 5 calls. Do we suspect there are plenty of things that we could do that will happen within a reasonable number of recursive calls? Yeah, it all depends on the nature of the problem, right? There's plenty of problems where we can say, you know what, this is really only going to get called 4 or 5 or 6 times, 10 times, 30 times, whatever. It's not going to be the end of the world. We're not going to even get close to the number of times where it actually is going to start impacting my life. So you don't worry about it. Make sense? All right, so your homework assignment, I'll put this up on Blackboard, is going to be to do, there's a tutorial that Google has set up for getting started with Android Studio. So I'm going to have you, it'll have you download Android Studio, which is kind of like Eclipse with a couple other things built into it. So it's good. It'll seem similar to you, familiar to you relative to Eclipse. And it takes you through writing a simple Android application that says hello world and then has like a button that takes you to a second screen. Just kind of an introduction to the Android ecosystem. So then what we're going to do the rest of the semester is we're going to continue introducing topics, but our solutions are going to be Android applications. They'll be cheesy, crappy interface Android applications, but rather than a text-based output, it'll be a mobile app. Make sense? All right, so I'll put that link up here in like 5 minutes, and then you can start working on it. It will take a little bit of time, so plan on spending, maybe a couple hours going through the tutorial. It takes a little bit of time, but it's more just monkey see, monkey do than a whole lot of it's introducing you to the tool. All right, I will see everybody on Tuesday.